Hello everyone, welcome back to the lecture series on digital signal processing, and we are studying discrete Fourier transforms. So this is continuation of the previous lecture. This is lecture 4. So we were solving problems, so let us continue to solve more problems. Find the endpoint DFT of the sequence x of n is equal to cos n omega naught, where omega naught is 2 pi k naught by n. So we will write x of n equal to cos, if I substitute omega naught here, I'll get 2 pi k naught n by n. Now cos theta can be written as half of e to the power of j theta plus e to the power of minus j theta, or in this case e to the power of j 2 pi k naught n by n plus e to the power of minus j 2 pi k naught n by n. And we know that the Twiddle factor Wn is e to the power of minus j 2 pi by n. So if we convert the exponential terms to Twiddle factor, we will get e to the power of, this is j 2 pi by n into n k naught. So we will get Wn to the power of minus n k naught plus, and here it is e to the power of minus j 2 pi by n can be written as Wn, and this one to the power of n k naught. So Wn to the power of n k naught. Now substitute in the formula of DFT, that is x of k is equal to summation n is equal to 0 to n minus 1 x of n Wn to the power of nk, or summation n is equal to 0 to n minus 1 half, I'll bring it out of the summation, Wn to the power of minus n k naught plus Wn to the power of n k naught, we have substituted in place of x of n, and then into Wn to the power of nk. So we will multiply and then split the summation. We will get half summation n is equal to 0 to n minus 1 Wn to the power of, when we multiply, I can take n common, so n into k minus k naught plus half summation n is equal to 0 to n minus 1 Wn to the power of n into k plus k naught. Now summation n is equal to 0 to L a to the power of n can be written as 1 minus a to the power of upper limit plus 1 by 1 minus a. So same thing we will use here. So we will get 1 minus Wn to the power of k minus k naught into capital N by 1 minus Wn to the power of k minus k naught plus half. Here also we will get 1 minus Wn to the power of k plus k naught into n by 1 minus Wn to the power of k plus k naught. This is because Wn to the power of k minus k naught acts as a, so this will be a to the power of n, summation a to the power of n. Similarly here Wn to the power of k plus k naught acts as a, so a to the power of n, we have used the formula. Now as we had discussed in the previous class, we have to check for what value of k the denominator can become 0. So here when k equal to k naught, the denominator can become 0, and in this second summation result k equal to minus k naught, then the denominator can become 0. So here we have two conditions. When k is not equal to k naught, this summation holds good, and when k equal to k naught, then we have to find out the solution to the summation, because the result whatever we have got will not hold good, because the denominator would have become 0. So in this case, when we look into the result what we have got, here we numerator we have got Wn to the power of k minus k naught into n, wn to the power of k minus k naught into n. So when we expand this Twiddle factor, we'll get e to the power of minus j 2 pi by n k minus k naught into n. N cancels, so we will get e to the power of minus j 2 pi k minus k naught, which is cos 2 pi k minus k naught minus j sin 2 pi k minus k naught. That means theta is integral multiple of 2 pi, so sin theta will be 0, cos theta will be 1. So the answer is 1. Similarly, in the second case also, wn to the power of k plus k naught into n is equal to 1. So here we would have got numerator is equal to 0 in both the cases, and denominator will become 0 when k equal to k naught in the first case and k equal to minus k naught in the second case. So second case, if k is not equal to minus k naught, that is one condition, and k equal to minus k naught, this is the second condition, because at k equal to minus k naught, this denominator will become 0. So when k is not equal to k naught, then this result will be 0 by some denominator which is 0. In this case also, when k is not equal to minus k naught, then denominator will not be 0, and this summation will be 0 by 1 minus wn to the power of k plus k naught. So 0 by anything, it is 0. Now, but when k equal to k naught in the first case, k equal to k naught, you substitute k is equal to k naught, wn to the power of 0 is 1, so 1 minus 1, it will be 0. So you will get 0 by 0. This solution, whatever we had got, you will get 0 by 0, so which cannot be taken. So that's why what we do is that this condition we are going to substitute in the original summation. So that is half summation n is equal to 0 to n minus 1. When I substitute k equal to k naught, then this will become 0. wn to the power of 0 is 1. So summation of 1 is upper limit minus lower limit plus 1, that is n minus 1 minus 0 plus 1. So n into half, we will get n by 2. Similarly, in this particular case also, when k equal to minus k naught, once again you can check denominator will become 0, or we will get 0 by 0, which we cannot consider because it is indeterminate. So that's why what we do, this condition we are going to substitute in the original summation. So half summation n is equal to 0 to n minus 1, wn to the power of 0 is 1, so here also we will get n by 2. So when we plot value of k is equal to k naught, at that time you have one sample whose amplitude is n by 2, and when k equal to minus k naught also, the sample amplitude is n by 2. So together we can write in terms of impulse function. So this particular sample, it can be written as delta of k minus k naught, because it exists at k equal to k naught, into n by 2. Similarly, this sample we can write it as n by 2 into delta of k plus k naught. So I'll take n by 2 common. So delta of k minus k naught plus delta of k plus k naught. Now k plus k naught, I can write it as plus k naught can be written as minus of minus k naught. So this can be written as n by 2 delta of k minus k naught plus delta of k minus k naught can be written as n minus k naught, because if we multiply with w n to the power of n k naught, then the value is 1 and it will not change the summation value. So this is the result. Similarly, the next question is find endpoint DFT of sin n omega naught. So this problem is same as the previous one, except that instead of cos we have sin here, and sin theta is e to the power of j theta minus e to the power of minus j theta by 2j. So we will write x of n as sin 2 pi k naught n by n, which is 1 by 2j into e to the power of j theta. So j 2 pi k naught n by n minus e to the power of minus j theta 1 by 2j I have written outside. So substitute in the formula n is equal to 0 to n minus 1 x of n. In place of x of n we have 1 by 2j. Yeah, now this I have to convert into Twiddle factor. So this will be wn to the power of minus n k naught minus wn to the power of n k naught, because e to the power of minus j 2 pi by n is wn. So wn to the power of k naught n, and this will be wn to the power of minus k naught n. So we have wn to the power of minus k naught n minus wn to the power of k naught n into wn to the power of nk. So we'll multiply and split the summation. So we'll get 1 by 2j summation 0 to n minus 1 wn to the power of n. I'll take common, I'll get k minus k naught. See, everything is same as the previous problem except that you have 1 by 2j in place of half, and instead of plus we have minus here, that's all. So minus 1 by 2j summation 0 to n minus 1 wn to the power of n k plus k naught. So this will be 1 by 2j into 1 minus wn to the power of k minus k naught into upper limit plus 1 by 1 minus wn to the power of k minus k naught minus 1 by 2j into 1 minus wn to the power of k plus k naught into n by 1 minus wn to the power of k plus k naught. So you can check wn to the power of k minus k naught into n is equal to 1. wn to the power of k plus k naught n is also equal to 1, and so you will get 0 by the term here, and the denominator of the first term, it is going to become 0 when k equal to k naught. So you have two conditions, k not equal to k naught and k equal to k naught. So when k not equal to k naught, the solution will be 0. K equal to k naught, you will have to substitute in the first summation, that is summation of 1. So the result will be n by 2j. Like previous case, we will get n for the summation, so n by 2j. And for the second case, like k equal to minus k naught, so k not equal to minus k naught, this is 0 because 0 by some denominator value. But when k equal to minus k naught, even denominator also becomes 0. So then we have to substitute this condition in the second summation, k equal to minus k naught. So this value will become 1. So summation of 1 is n. So the result will be minus n by 2j, because we are multiplying with minus 1 by 2j. So together we can write the result as x of k is equal to, I'll take n by 2j common. This will be delta of k minus k naught minus delta of k plus k naught, which can be written as n by 2j delta of k minus k naught minus delta of k plus k naught can be written as minus k naught, minus of minus k naught, and minus k naught can be written as n minus k naught. So you have to remember, for cos 2 pi n k naught by n, the DFT result what you got is n by 2 into delta of k minus k naught plus delta of k plus k naught, and for sin 2 pi n k naught by n, you got the DFT as n by 2j into delta of k minus k naught minus delta of k plus k naught. These results can be used in the problems where cos theta and sin theta are present in the expressions. Then you need not waste your time by calculating the DFT of cos theta and sin theta. Next, compute the DFT of the sequence defined by x of n is minus 1 to the power of n for n odd and n even. So first write the formula of DFT. X of k is equal to summation n is equal to 0 to n minus 1 x of n wn to the power of nk. And here x of n is minus 1 to the power of n. So substitute minus 1 to the power of n. I'll take n common here. So we'll get some summation minus 0 to n minus 1 minus wn to the power of k whole to the power of n. Now this is in the form summation n is equal to 0 to L a to the power of n. So you will get 1 minus a to the power of upper limit plus 1 by 1 minus a. So we can expand this as 1 minus wn to the power of k is minus 1 into wn to the power of k whole to the power of n. So minus 1 to the power of n wn to the power of kn by 1 minus of minus is plus wn to the power of k. And we know wn to the power of kn is 1, because e to the power of minus j 2 pi n k by n gets cancelled. You will get e to the power of minus j 2 pi k, which is cos 2 pi k minus j sin 2 pi k, which is 1. So this is 1 minus 1 to the power of n by 1 plus wn to the power of k. Now the first condition when n is odd. So when n is odd, then x of k will be 1 minus 1 to the power of n. N is odd means minus 1 to the power of n will be minus 1. So x of k will be minus of minus 1 by 1 plus wn to the power of k, that is 2 by 1 plus wn to the power of k. Now you check the condition for which the denominator will become 0. Wn to the power of k, if it becomes minus 1, then the denominator is 0, and that will arise when wn to the power of k is minus 1. So wn to the power of k is minus 1, that means k is equal to n by 2. Okay, you check e to the power of minus j 2 pi by n into n by 2, 2 cancels, n cancels, this will be e to the power of minus j pi, which is minus 1. So when k equal to n by 2, then wn to the power of k is minus 1, and that time the denominator will become 0. So this holds good, 2 by 1 plus wn to the power of k holds good when k is not equal to n by 2. Okay, but because n is odd, this condition will not arise. Why? Because n by 2 should be an integer, and because n is odd, n will not be divided by 2. So obviously k equal to n by 2 condition will not arise for when n is odd. So for all the values of the DFT, x of k is equal to 2 by 1 plus wn to the power of k for all values of n when n is odd. But consider the case when n is even. When n is even, minus 1 to the power of n will be 1. Then x of k will be 1 minus 1 by 1 plus wn to the power of k. So this will be 0 by 1 plus wn to the power of k. Now here this condition may arise. We will check. So when k is not equal to n by 2, the result is 0, because wn to the power of k will not be equal to minus 1. So 0 by something will be 0. But when k equal to n by 2, in this case this condition will arise because n is even number, and even number divided by 2 will give us an integer, a positive integer we are going to get. So this condition will arise when n is even, and in this case when k equal to n by 2, we know wn to the power of k will be minus 1, that means denominator will also become 0. And we now know what we have to do. When denominator becomes 0, then the particular condition we have to substitute in the summation formula, summation itself. So we will substitute summation n is equal to 0 to n minus 1 minus wn to the power of n by 2. When I substitute, wn to the power of n by 2 is minus 1. So minus of minus 1 will be plus 1. and summation of plus 1 is upper limit minus lower limit plus 1, that is n. So the result, when we combine these two, we will get x of k is equal to n for delta of k minus n by 2. That means at k equal to n by 2, you have a sample whose amplitude is n. For all other values of k, x of k is equal to 0. So hope you have understood why we have not taken k, the condition k equal to n by 2 or k not equal to n by 2 when n is odd. K should be integer value, positive integer value, that is it ranges from 0 to n minus 1. But n by 2, when I consider n is odd, n by 2 will not be an integer value. But when n is even, n by 2 will be a integer. Next we have to find out the DFT of delta of n and delta of n minus n naught. So we know that delta of n is the impulse function and it is 1 when n is equal to 0 and 0 for all other values of n. Thus, if we substitute this in the formula of DFT, that is n is equal to 0 to n minus 1, x of n, in place of x of n we will substitute delta of n, wn to the power of nk. Here n ranges from 0 to n minus 1, n is ranging from 0 to n minus 1, and this product delta of n into wn to the power of nk will exist only at n is equal to 0, because delta of n exists only at n is equal to 0 and all other values of n, delta of n is 0. So 0 into wn to the power of nk will be 0. So only at n equal to 0 this product exists. So substitute n is equal to 0. So at n equal to 0 delta of n is 1, and at n equal to 0 wn to the power of nk, wn to the power of 0 is 1. So the DFT of delta of n is 1. Next, when x of n is delta of n minus n naught, delta of n minus n naught will be 1 at n equal to n naught and 0 for all other values of n. Now when this is substituted in the DFT formula, summation n is equal to 0 to n minus 1 delta of n minus n naught wn to the power of nk. Once again you can see in the range 0 to n minus 1, delta of n minus n naught exists only when n is equal to n naught. Only at this particular point you have a sample of amplitude 1. For all other values of n, delta of n minus n naught is 0. So you substitute the condition, this particular product exists only at n equal to n naught. So you substitute n is equal to n naught. So at n equal to n naught, delta of n minus n naught is 1, and this will be wn to the power of n naught k when you substitute n is equal to n naught. So the DFT of delta of n minus n naught is wn to the power of n naught k. Next we have to find the DFT of x of n equal to cos n pi by 4 for n is equal to 4, and then plot the magnitude and phase also. So x of n, it is given that n is equal to 4, so we will substitute small n is equal to 0 to n minus 1. So in this case n is equal to 0 to 3. So when n is equal to 0, cos 0 is 1, n is equal to 1, we will get cos pi by 4, that is 1 by root 2. N is equal to 2, we will get cos pi by 2, that is 0. N is equal to 3, we will get cos 3 pi by 4, that is minus 1 by root 2. So x of k is summation n is equal to 0 to 3 x of n w4 to the power of nk. So when we expand the series, we have x of 0. Next we substitute n is equal to 1. So we get x of 1 w4 to the power of k, then x of 2 w4 to the power of 2k plus x of 3 w4 to the power of 3k. So x of 0 is 1, x of 1 is 1 by root 2, x of 2 is 0, x of 3 is minus 1 by root 2. Now k ranges from 0 to 3, that is 0 to n minus 1. So first substitute k equal to 0. So we will get 1 plus 1 by root 2 minus 1 by root 2, that is 1. Next substitute k equal to 1. So 1 plus 1 by root 2 w4 to the power of 1 by 1 minus 1 by root 2 w4 to the power of 3. Now if you remember, the Twiddle factor w4 to the power of 0 is 1, w4 to the power of 1 is minus j, w4 to the power of 2 is minus 1, and w4 to the power of 3 is plus j. So this result will be 1, w4 to the power of 1 is minus j, so minus j by root 2, minus w4 to the power of 3 is j, so you will get minus j by root 2. So 1 minus 2 by root 2j, that is root 2j. Now x of 2 is 1 plus 1 by root 2 w4 to the power of 2. In place of k you substitute 2, so minus 1 by root 2 w4 to the power of here 3 to the 6 we will get. W4 to the power of 2 is minus 1, so minus 1 by root 2. W4 to the power of 6 can be written as 4 plus 2, so w4 to the power of 6 is equal to w4 to the power of 2, that is minus 1, so minus of minus plus 1 by root 2, so we will get 1. Next substitute k equal to 3. So we will get 1 plus 1 by root 2 w4 to the power of 3 minus 1 by root 2 w4 to the power of 9. We have substituted k equal to 3 in this equation. So 1 w4 to the power of 3 is j, so plus j by root 2. W4 to the power of 9 is 4 plus 4 plus 1. 9 is 4 plus 4 plus 1. So w4 to the power of 9 is equal to w4 to the power of 1, that is minus j. So minus of minus plus j by root 2. So we will get 1 plus 2 by root 2j, that is root 2j. So we got x of k equal to 1 minus j root 2, 1 plus j root 2. So this is about DFT. Now we have to plot the magnitude and phase. So to plot the magnitude and phase, we have to convert the complex numbers which are in rectangular form to polar form, or magnitude is given by square root of a square plus b square. If a plus jb is the complex number, then magnitude is square root of a square plus b square, and phase is given by tan inverse of b by a. So when you convert, root 3 is the magnitude, and tan inverse minus root 2, tan inverse of minus root 2 will be, if you take it in degrees, it is minus 54.73 degrees. In radians it is minus 0.9553. So I will take it in degrees. Minus 54.73 degrees, and here it will be root 3 into 54.73 degrees. So when we plot, you have x of k is equal to 1 angle 0, root 3 angle minus 54.73 degrees, 1 angle 0, and root 3 angle 54.73 degrees. So magnitude, if you plot, then at k equal to 0 magnitude is 1, k equal to 1 the magnitude is root 3 is 1.732, k equal to 2 once again the magnitude is 1, k equal to 3 magnitude is root 3. So this is the magnitude plot. Similarly phase, k equal to 0 it is 0, k equal to 1 it is minus 54.73 degrees, k equal to 2 it is 0, and k equal to 3 it is plus 54.73 degrees, and this is the phase plot. So after getting the DFT, you have to convert the complex numbers into polar form and then plot the magnitude and phase separately. So next, let x of n be a real sequence. So here x of n is given as a real sequence of length n. Endpoint DFT is given by x of k. And what you have to do, you have to find out, show x of n minus k is equal to conjugate of x of k, and x of 0 is real, and x of n by 2 is real. This you have to show. Okay, so we take the formula of x of k, that is summation n is equal to 0 to n minus 1 x of n wn to the power of nk. We have to take conjugate of x of k, so apply conjugate on both the sides. So conjugate of x of k is equal to summation 0 to n minus 1 x of n wn to the power of nk whole conjugate, and if I bring conjugate inside, we'll get summation 0 to n minus 1 conjugate of x of n into wn to the power of, here wn to the power of nk is e to the power of minus j 2 pi nk by n, that is cos theta minus j sin theta. Its conjugate will be plus or e to the power of plus j 2 pi nk by n. So here it will be represented as wn to the power of minus nk. Now conjugate of x of n is how much? X of n is real sequence, so conjugate of x of n will be equal to x of n because x of n is real. So this can be written as summation 0 to n minus 1 x of n wn to the power of, here minus nk is there, so we will write n into minus k, which we can write it as so here what I will do is I will multiply with wn to the power of n capital N. So wn to the power of n capital N is what? E to the power of minus j 2 pi n by capital N, which is e to the power of minus j 2 pi n or 1. So when we multiply, what will we get? Summation 0 to n minus 1 x of n wn to the power of, if I take n common, I'll get n minus k. Why did I multiply with n? Because you can see we have to prove that conjugate of x of k is equal to x of n minus k. So that's why I multiplied with wn to the power of n. So now this is equal to x of n minus k. When you compare it with the formula of the DFT, you can see all the terms are same. In place of k, we have n minus k. So instead of writing x of k, we write x of n minus k. And we have proved that conjugate of x of k is equal to x of n minus k. Now the second is we have to show that x of 0 is real. So we take the formula of the DFT, that is x of k is equal to n is equal to 0 to n minus 1 x of n wn to the power of nk. Now if I have to get x of 0, I have to substitute k is equal to 0. So x of 0 is equal to summation n is equal to 0 to n minus 1 x of n. When I substitute k equal to 0, we'll get wn to the power of 0, which is 1. So summation of x of n. X of n is real numbers, real sequence. So summation of the real elements in the real sequence will be real, or x of 0 is real. Why? Because x of n is a real sequence. Next, x of n by 2 is real. So once again, in the formula of DFT, we will substitute k equal to n by 2 because we have to get x of n by 2. So we will get summation n is equal to 0 to n minus 1 x of n, wn to the power of n. In place of k, we will substitute n by 2. So here we will get summation n is equal to 0 to n minus 1 x of n. Now what is wn to the power of n into n by 2? In the previous example we had solved, wn to the power of n by 2 is e to the power of minus j 2 pi by n into n by 2. So 2 cancels, n cancels, it is e to the power of minus j pi n, that is equal to minus 1 to the power of n. E to the power of minus j is, j pi is minus 1, to the power of n we have to write. So this summation of x of n into minus 1 to the power of n is alternate addition and subtraction of the samples of x of n, and we know x of n is real, therefore x of n by 2 is real. Next, find the z transform of the sequence x of n is equal to 0.50, 0.50 using z transform, and then find DFT. So x of n is given. What is this formula of z transform? To find the z transform, x of z is summation n is equal to minus infinity to infinity x of n z to the power of minus n. So here it is 4 samples are there. So 0 to n is equal to 0 to 3 x of n z to the power of minus n, and we expand the summation, we will get x of 0 plus x of 1 z to the power of minus 1 plus x of 2 z to the power of minus 2 plus x of 3 z to the power of minus 3, which is equal to 0.5. X of 1 is 0, x of 3 is 0, so plus 0.5 z to the power of minus 2. So this is the z transform of the sequence. Now we have to find out the DFT. What is the formula of DFT? X of k is equal to summation 0 to n minus 1 x of n wn to the power of nk, or it is summation n is equal to 0 to n minus 1 x of n. Wn to the power of nk is nothing but e to the power of minus j 2 pi nk by n. In this example, 4 samples are there. We take n is equal to 4. So this will be n is equal to 0 to 3 x of n e to the power of minus j 2 pi by 4 nk. Now when we compare it with the DFT formula, you can see that instead of z, if we replace z with e to the power of j 2 pi by 4k, then we are going to get the same summation, right? So this one and this one, if we compare, if z is equal to e to the power of j 2 pi k by 4, then we are going to get the same result. Because if I expand this, I'll get x of 0, x of 1 and x of 3 are zeros, so x of 2 e to the power of minus j 2 pi into 2k by 4. So we will get 0.5 plus 0.5, here e to the power of minus j pi k, that is 0.5 plus 0.5 into minus 1 to the power of k we are going to get. So this is after expanding the summation. But if I had substituted z is equal to e to the power of j 2 pi k by 4 in equation 1, then I would have got x of e to the power of j 2 pi k by 4 equal to 0.5 plus 0.5 z, that is e to the power of j 2 pi k by 4 to the power of minus 2, which is 0.5 e to the power of minus j pi k, and we get 0.5 plus 0.5 into minus 1 to the power of k. So you can see we got the same value, that is equation 2 and equation 4 are same. This will give us the DFT. So you have to substitute k equal to 0 to 3. So when k equal to 0, minus 1 to the power of 0 is 1. So we will get 0.5 plus 0.5, that is 1. And when k equal to 1, that is x of 1 will be 0.5 minus 0.5. X of 2, substitute k equal to 2. So minus 1 to the power of 2 is 1. So 0.5 plus 0.5 will get 1. And x of 3, minus 1 to the power of 3 is minus 1. So we will get 0. So we got x of k equal to 1, 0, 1, 0. So here what we have to understand is that if you substitute z is equal to e to the power of j 2 pi by n into k, z transform will give us the DFT. Next we have to solve or find the IDFT of the sequence x of k. Now you can see here 8 samples are present, that means n is equal to 8, and we have to find the IDFT. So what is the formula of IDFT? X of n. What is you mean by IDFT? Inverse discrete Fourier transform. You have to find out the time domain sequence. So x of n is equal to 1 by n summation k equal to 0 to n minus 1 x of k wn to the power of minus nk. Or in this case n is equal to 8. So we have 1 by 8 summation k equal to 0 to 7 x of k w8 to the power of minus nk. So we can see that except when k equal to 1 and k equal to 7, all other samples are 0. So in the summation we can write this as 1 by 8 into, I'll substitute k equal to 1 and 7. So x of 1 is, okay, first let me write x of 1 w8 to the power of minus n, because k is 1, plus x of 7 w8 to the power of minus 7n. And for all other values of k, because x of k is 0, here we are not writing it. So this will be 1 by 8 into 2 root 2 1 minus j w8 to the power of minus n plus 2 root 2 into 1 plus j w8 to the power of minus 7n. And n ranges from 0 to n minus 1. So in this case 0 to 7. Now we need to find out the Twiddle factors. So normal Twiddle factors first let us find, and w8 to the power of minus, that means conjugates we'll have to take them. So first let us find out 8 Twiddle factors. w8 to the power of 0 is 1. Next you have here w8 to the power of 1, 2, 3, w8 to the power of 4 is minus 1, w8 to the power of 5, 6, 7. we know that the Twiddle factors, they lie on circle of unit radius and they are separated by phasor angle of 2 pi by n. In this case 2 pi by 8 or pi by 4, that is 45 degrees. One value I will show you how to calculate. WA to the power of 1 is e to the power of minus j 2 pi by 8 to the power of 1, so into 1. This is e to the power of minus j pi by 4, which is cos pi by 4 minus j sin pi by 4, or 1 by root 2 minus j 1 by root 2. So WA to the power of 1 is 1 by root 2 minus j 1 by root 2. WA to the power of 2 will be equal to W4 to the power of 1, that is minus j. WA to the power of 6 is equal to W4 to the power of 3, that is plus j. Now W8 to the power of 3 is cos 3 pi by 4 minus j sin 3 pi by 4, that is minus 1 by root 2 minus j 1 by root 2. So I'll write here directly. This is minus 1 by root 2 minus j 1 by root 2. W8 to the power of 5 is cos 5 pi by 4 minus j sin 5 pi by 4, that is minus 1 by root 2 plus j 1 by root 2. You can see these two are conjugates of each other. And similarly W8 to the power of 7 is cos 7 pi by 4 minus j sin 7 pi by 4. So this will also be conjugate of this, that is 1 by root 2 plus j 1 by root 2. Now substitute n equal to 0 here. 1 by 8 2 root 2 into 1 minus j. When you substitute n is equal to 0, W8 to the power of 0 is 1, so plus 2 root 2 into 1 plus j. So 2 root 2 plus 2 root 2 is 4 root 2 by 8. So we'll get root 2 by 2 or 1 by root 2. Next substitute n is equal to 1. So we'll get 2 root 2 1 minus j W8 to the power of minus 1 plus 2 root 2 1 plus j W8 to the power of minus 7. So 1 by 8 2 root 2 1 minus j W8 to the power of minus 1. W8 to the power of minus 1 is conjugate of W8 to the power of 1. So W8 to the power of minus 1 will be 1 by root 2 minus j 1 by root 2 plus j 1 by root 2. So 1 by root 2 I'll take common. So I'll write 1 plus j. Next here plus 2 root 2 into 1 plus j. W8 to the power of minus 7 is conjugate of W8 to the power of 7. So I'll take 1 by root 2 common and this will be 1 minus j. So W8 to the power of minus 7 will be 1 by root 2 minus j 1 by root 2, conjugate of W8 to the power of 7. You have to keep that in mind. So root 2 cancels. Here also root 2 cancels. 1 minus j into 1 plus j. Here also 1 minus j into 1 plus j. So you will get 4 into 1 minus j into 1 plus j. So 4 by 8. So half into 1 minus j into 1 plus j. So when we multiply we'll get 1 plus j minus j plus 1, that is 2 by 2 or 1. Similarly if we solve x of 2 will be 1 by 8, 2 root 2 into 1 minus j w8 to the power of, now I am substituting 2, so minus 2, plus 2 root 2 into 1 plus j into w8 to the power of, when I substitute 2 I will get minus 14 here. So w8 to the power of minus 14 is equal to, 14 can be written as 8 plus 6. So w8 to the power of minus 14 is equal to w8 to the power of minus 6. w8 to the power of minus 6 is conjugate of w8 to the power of 6, so it is minus j. w8 to the power of minus 2 is conjugate of w8 to the power of 2, that is plus j. So w8 to the power of minus 2 is plus j, w8 to the power of minus 14 is minus j. So the answer what we get will be 1 by root 2. Similarly, substitute n is equal to 3. So we'll get 1 by 8, 2 root 2, 1 minus j, w8 to the power of minus 3, plus 2 root 2, 1 plus j, w8 to the power of minus 21 we will get. w8 to the power of minus 3 is conjugate of w8 to the power of 3, so minus 1 by root 2 plus j 1 by root 2 you will have. w8 to the power of minus 21, 21 is can be written as 16, that is multiples of 8, 16 plus 21 is 16 plus 5, so w8 to the power of minus 21 will be equal to w8 to the power of minus 5, and w8 to the power of minus 5 is conjugate of w8 to the power of 5, so it will be minus 1 by root 2 minus j 1 by root 2, and when you perform the simplification you will get 0. Now substitute n is equal to 4. So when I substitute n is equal to 4, I'll get 1 by 8 into 2 root 2 into 1 minus j, w8 to the power of minus 4, plus 2 root 2 into 1 plus j, w8 to the power of minus 4 7s are 28. w8 to the power of minus 28, 28 can be written as 24 plus 4, 24 because 24 is multiple of 8, so 24 plus 4, so w8 to the power of minus 28 is equal to w8 to the power of minus 4. So when we substitute, the result we get will be minus 1 by root 2. Next, n is equal to 5. If I substitute, we'll get 1 by 8, 2 root 2 into 1 minus j, w8 to the power of minus 5, plus 2 root 2 into 1 plus j, w8 to the power of minus 7 5s are 35. Now w8 to the power of minus 35, the 35 can be written as 32 plus 3, so w8 to the power of minus 35 is equal to w8 to the power of minus 3, and the result we get will be minus 1. X of 6, substitute n equal to 6, so w8 to the power of minus 6 plus 2 root 2 1 plus j, w8 to the power of minus 42. Once again here 42 can be written as 40 plus 2, so w8 to the power of minus 42 is equal to w8 to the power of minus 2. So the result is minus 1 by 2. Last, substitute n is equal to 7. So 2 root 2 1 minus j, w8 to the power of minus 7, plus 2 root 2 1 plus j, w8 to the power of minus 49. wa to the power of minus 49. 49 can be written as 48 plus 1. So wa to the power of minus 49 is equal to wa to the power of minus 1. And we get 0. So x of k equal to x of n equal to when n equal to 0, it is 1 by root 2, next 1, next 1 by root 2, next 0. So 1 by root 2, 1, 1 by root 2, 0, minus 1 by root 2, minus 1, minus 1 by root 2, 0. Hope you have understood this problem. From this, what do you understand is the Twiddle factor which you use in IDFT, the value will be conjugate of the value which you use in DFT, or in other words, wa to the power of minus 1 will be conjugate of wa to the power of 1, etc. Okay, then these problems we will solve in the next video lecture. Thank you and have a good day. I hope you have understood the problems what we have solved today. If you have any doubts, you can leave it in the comment box. Thank you.